What if you could change your brain just by learning something new? Inside your head are around 86 billion neurons, linked by more than 100 trillion synapses. That amounts to roughly 10 times the people on Earth in a single city, a city with an absurd number of connecting roads. For decades, we've known that learning changes those connections, but now we're finally seeing how. It's called neuroplasticity, and it can help improve our focus, memory, learning ability, and even change the structure of our brain. As life gets more distracting and our free time seems to have disappeared, more and more people are turning to AI to access information. But over time, that can make it feel harder to remember things or even to learn new skills. Spending time learning something new or even studying can flip that by using neuroplasticity to our advantage. And studies are proving that there's more than one way to change our brain. One approach increases our brain's grey matter, while another builds new pathways between neurons. But how does learning actually pull this off? And what are the 4 biggest upgrades you can make to your brain? Hi, I'm Teresa Orr. Welcome back. If you're new to my channel, don't forget to like and subscribe to stay in the loop. So we often hear a lot about how we can boost our brain with exercise or healthy diets. But what about studying or learning a new skill? Specific neurons are activated when we challenge our brain. What if we could take something that we've just learned and use it to force our brain to build a new pathway between those neurons to make the information actually stick so we could recall it later? Well, it turns out we can. It's called neural pathway formation, and it's brain upgrade number 1. A neural pathway is basically just a route that your brain can run. It's like a chain reaction. Neuron A triggers neuron B, which triggers neuron C, and that pattern becomes the route. Think of it like building a new dirt road in our brain city. When we first start learning, that route is going to feel bumpy and unstable. But the more we practice, the more our brain reinforces that new pathway until it becomes automatic, and we can recall that new skill or information on demand. If you want to build neural pathways that actually change your brain, you need a certain kind of practice. Currently, active recall is one of the best ways to build pathways faster because it forces your brain to strengthen that new neural network. Active recall means producing something instead of just reading or watching. Things like answering practice questions, using flashcards, or even explaining a new concept to a friend. A 2006 study found that students that actively tested themselves remembered 61% of the material 1 week later, compared to just 41% for students that just reread the information. What makes this so significant is that the active testing group only read the information 3 times, but those that reread it did so 14 times. So if you want to boost your brain by forming new pathways, the rule is simple. Don't just look, practice and self-test. Once you've created those new neural pathways, the next brain upgrade will make them faster. It's called myelination, and it's your brain turning that rough dirt road between neurons into a smooth highway. Myelination is insulation wrapped around axons. They're the long fibers that neurons use to send signals. Unmyelinated signals can move around 0.5 meter to 2 meters per second, but myelinated signals can reach up to more than 100 meters per second. That speed and timing is a huge part of why a new skill can become faster and smoother with more practice. One of the clearest places we see this is in motor learning. At the start, the neural pathway exists, but it's inefficient. You can do the skill, but it doesn't feel clean or easy. That's because the signal along that neural pathway is slow and noisy. So how do you make that neural pathway faster without actually changing the information that's traveling along it? You upgrade the wiring around it with myelin. But this upgrade doesn't happen just because you do something once. Your brain has to believe that neural pathway is worth the upgrade. So what convinces it? Repetition, challenge, and consistency. First, you need enough correct repeats that the same neural pathway will light up. Second, the practice has to be difficult enough that it demands attention. Third, the practice has to happen often enough that your brain doesn't think it's a one-off. Once a neural pathway is myelinated, the new skill can run with less effort, even when you're tired, stressed, or under pressure. If you want to get the most out of this brain change, it's not about longer practice sessions, it's about smarter practice sessions. Short practice over many days gives your brain a repeated signal that this neural pathway matters. It's like when you learn how to drive. At first, every movement is conscious, but later on, those same actions, things like changing gear or turning the indicator on, happen automatically, running in the background. That's neural pathway formation plus myelination working together. And it's closely linked with our cognitive function as we age. But speeding up our neural pathways isn't the final upgrade. What if your brain could also change which area or neural pathways do the work? so the whole system could run more efficiently. That's called functional reorganization and brain upgrade number 3. Our brain is only about 2% of our body weight, but it uses up to 20% of our energy, so efficiency matters. When we're learning something new, our brain likes to recruit support systems to get the work done, especially the areas involved in attention and control. That's why when we first start learning something new, it feels mentally draining. Because it is. We can do the new thing, but it takes a lot of effort to stay focused, keep the steps in order, and not mess it up. So how can our brain make it feel easier? Well, by moving the workload around. At the beginning, our brain relies heavily on the conscious control system. We have to think carefully through every step. But with practice, our brain shifts that workload onto specialized neural pathways, and that can make the skill feel automatic. According to a 2006 study, brain scans show a simple pattern. Early on, lots of regions light up because our brain is working hard. Later on, with practice, activation decreases across many of those regions, including the prefrontal, parietal, and occipital cortex, even as performance improves. That combined decrease in effort and increase in performance is known as neural efficiency. And it's not just when we're practicing or studying. One study found that after learning, the brain's resting activity pattern, what your brain does when it's doing nothing, changed in the areas involved in that new skill. In other words, learning can also reshape the background wiring of our brain. So how can you trigger this functional reorganization on purpose? You basically want to give your brain a reason to stop relying on full attention mode and build a more efficient system. There are 3 ways to do that. First, practice until it's stable and then add variability. If you only practice in one exact way, your brain gets very good at that and then falls apart when anything changes. So once you're consistent, change the conditions. That pushes your brain to reorganize around the underlying new skill. Second, interleave instead of blocking. Block practice can feel easier. It's where we do the same thing over and over again. Interleaving is where we mix different subjects, topics, or types of problems. And it forces your brain to use and train the networks that are in control of switching. Over time, that switching becomes smoother and more efficient. Third, add performance pressure to your practice. If you only ever practice something in calm conditions, then you're not training the system to be able to function under real life conditions. So build in timed practice, doing it when you're tired, not exhausted, and doing it with minor distractions. Not to make it miserable, but functional reorganization is partly about being able to make that skill hold up when your attention isn't perfect or conditions aren't ideal. So if we go back to our analogy of neural pathway formation and myelination, building new roads and upgrading them into highways, functional reorganization reroutes the traffic so that our brain city runs better. And once that system is running more efficiently, the last upgrade is where our brain tissue itself changes. That's grey matter. Grey matter is basically our brain's processing suburbs. It's where a lot of our cells, branching connections, and wiring live. So when grey matter changes, it's not just, I got good at something. It's your brain physically reshaping the parts that do the work. And we can see it in MRI studies. In one well-known study, adults learned how to juggle. And after about 3 months, their brain scans showed that their grey matter had increased in the areas processing complex visual motion. Then, when they stopped practicing, those increases faded back down, meaning the change was real, but also a case of use it or lose it. And it's not limited to juggling. In another study, researchers scanned medical students' brains 3 times, before months of intense learning, right after the exam, and then again 3 months later. During the learning period, grey matter increased significantly in the posterior and lateral parietal cortex on both sides of the brain. So this isn't just a metaphor. Over weeks to months, sustained learning or studying can be big enough that we can measure structural changes in our brains. If you keep demanding a new skill, your brain can start allocating more building material to the areas that support it. So how do you trigger this upgrade on purpose? A simple recipe is to pick a skill that is genuinely new. Train it consistently, for weeks, not days. Keep it challenging, and progress the difficulty so your brain keeps getting the message. Across these upgrades, the pattern is pretty wild. You can build new pathways, make them smoother and faster, reorganize them so they run more efficiently, and over time even shift the structure of your brain tissue itself, all from learning.